On a summer day in 1951, naval aviation faced a quiet catastrophe. Jets were arriving faster than carriers could safely recover them. Pilots who missed the wires risked plowing into parked aircraft, burning hangars, or worse, the entire ship's flight deck. At lunch, a Royal Navy captain sketched a simple, radical change. Cant the landing lane away from the ship's centerline so a missed arresting wire could be converted into a safe go-around. That idea, later called the angled flight deck, would be trialed within a year and adopted worldwide, reshaping carrier operations and saving countless lives. By the close of the Second World War, the carrier had matured into the decisive naval weapon. But the move from piston props to jets changed everything. Approach speeds rose, landing runs shortened, and aircraft became heavier. A straight flight deck, inherited from the propeller era, meant a missed hook, a bolter, risked hitting aircraft parked forward, or engaging barriers that could send the plane and crew into catastrophic fires. Training hours were expensive, and losses mounting. Deck crews faced repeated fatal mishaps during recovery cycles. The Royal Navy and U.S. Navy both studied fixes, stronger barriers, optical landing aids, and new handling procedures. Yet the fundamental risk, a straight-line landing path ending amid parked aircraft, remained. These operational limits set the stage for a design pivot in 1951. On 7 August 1951, Captain, later Rear-Admiral, Dennis R. F. Cambell, recorded an idea that had been gestating since studies begun in 1944-45. Make the landing path diverge from the ship's fore-aft centerline. The concept was elegant. Dedicate an angled runway aft so that a failed arrestor engagement could be converted into power and a safe go-around without crossing the forward parking area. Cambell worked with civilian aerodynamicists and the Royal Aircraft Establishment to test the geometry. The proposal was low-tech on paper, but high-value in consequence. It eliminated the dead-end landing and allowed concurrent launches and recoveries, a decisive operational improvement. Cambell's role is acknowledged in naval histories and in his obituaries. Trials followed quickly. In 1952, the angled layout was trialed experimentally, initially by painting an angled centerline and conducting touch-and-go trials, then by fitting a sponsoned extension to permit full arrested landings on the new skewed axis. The U.S. carrier USS Antietam and British carriers were early testbeds. By late 1952, both navies had filmed and recorded the results. Tests validated what sketches promised. Pilots could intentionally bolter and rejoin without crossing the forward park, and deck movement was simplified. Within a few seasons, the data and operational feedback persuaded staff officers to move from experiment to retrofit and new build design choices. These trials form the core documented arc from idea to fleet standard. Turning a mess table sketch into a serviceable landing surface required pragmatic engineering. Naval architects solved two linked problems: where to cut and how to support. Painted trial lines proved the geometry, But full arrested landings demanded strengthening, new sponsons or deck extensions, and redesigned deck edge structures to clear proplosh and jet blast. Shipyards fitted reinforcing beams, altered island positions on some classes, and reworked elevator locations so parked wings no longer intruded into the angled lane. Importantly, modifications were kept modular. Temporary sponsons and painted centerlines reduced risk during trials and allowed operational squadrons to evaluate the concept without committing to irreversible rebuilds. The engineering work was iterative. Close cooperation between deck officers, pilots, and shipbuilders turned a simple concept into a repeatable ship alteration procedures, enabling fleets to test and then adopt the change with minimal interruption to deployments. The angled deck's promise depended on pilot discipline and revised deck procedures. Squadrons rewrote approach briefings. The concept of a deliberate bolter using full power to climb away after a missed arrestor became formalized. Landing signals officers learned new visual cues, and carrier air traffic control established revised circuits to keep bolting aircraft clear of launching aircraft and parked wings. Crucially, simulators and shore-based trials allowed pilots to rehearse go-around profiles under varying wind and night conditions before attempting deck recoveries at sea. The human factor, fatigue, deck stress, night operations remained. But by converting an immediate catastrophic failure into a recoverable event, the angled deck reduced the split-second dilemmas that killed aviators and sailors. Welders and signalmen didn't produce the idea. Naval aviators lived its life-saving consequence. Adoption of the angled deck produced measurable operational shifts. Carriers could recover and launch aircraft concurrently, raising sortie tempo and reducing recovery bottlenecks during high-intensity operations. The ability for a missed engagement to become a safe go-around lowered the incidence of deck collisions and fire-damaging incidents, and it simplified emergency response by reducing multi-aircraft wreck scenarios. Fleet staff noted improved flexibility. Air Group commanders could plan tighter launch recovery cycles, and risk calculus for night and poor visibility operations changed. International navies observed and adapted the innovation quickly. The angled deck moved from experimental paint lines to an accepted feature of modern carrier design, altering carrier doctrine and permitting jets to operate from afloat platforms far more safely than the straight deck of the piston era had allowed. Night recoveries were the crucible of carrier aviation. Visual cues were poor. Deck crews worked by floodlight, and a single missed hook could turn a dark deck into an inferno. Before the angled deck, night bolters risked sliding into parked lines of aircraft or colliding with the forward barricades used as a last resort. The angled lane changed that calculus. Pilots could be trained to accept a bolter at night as a planned event and execute a controlled climb-out to the established circuit. Landing signals officers refined night signals to match the new geometry. The result was not fireworks or sudden headlines, but a steady decline in catastrophic night deck incidents. Where once night-arrested recoveries demanded extreme conservatism and curtailed operations, commanders found they could press harder, conduct night strikes with greater confidence, and keep carriers on station longer without the crippling risk of multi-aircraft deck disasters. Innovation at sea rarely stays local. Word of the angled deck's operational utility spread through naval attachés, fleet exercises, and exchange pilots. Observers from Allied navies watched painted trials and sponson trials and returned with reports emphasizing simultaneous launch recovery benefits and lowered deck catastrophe risk. Aircraft manufacturers adjusted arrestor hook travel and undercarriage geometry to match steeper, faster approaches. Carrier design bureaus placed angled deck geometry on new build requirement lists. Even navies that began with conservative skepticism, concerned about deck edge clearances and elevator rework, found the trade-off favorable. The change demonstrates how a pragmatic, low-cost modification can become doctrinal. Carrier fleet manuals were rewritten, training syllabi updated, and the angled deck passed from experimental footnote into accepted best practice across multiple navies within a single decade. When crashes did occur, they were less likely to cascade into multi-aircraft catastrophes that overwhelmed damage control teams. Angled decks isolated the risk. A struck aircraft usually stayed aft or was thrown clear of forward parking, limiting fuel-fed fires and allowing firefighting teams to contain incidents more rapidly. Admiralty boards and accident inquiries in this period shifted their focus. Investigators noted fewer complex deck conflagrations and more single aircraft incidents with clearer root cause chains. That clarity simplified corrective action, pilot technique, wire maintenance, or signal procedures, rather than sparking fleet-wide structural debates. The legal and procedural consequence was important. Safer recoveries produced narrower, actionable findings and faster dissemination of corrective practices across squadrons and ship classes, accelerating the learning loop from incident to remedy. The angled deck altered more than landings. It reshaped how commanders planned strikes. Air group commanders could now schedule denser cycles of launches and recoveries without the previous safety buffers that a straight deck demanded. Task group planners exploited the higher sortie tempo for sustained strikes, close air support, and rapid cap rotations. Reconnaissance and strike packages were timed with tighter windows because commanders had confidence that recovery throughput would not collapse if a pilot bolted. This doctrinal shift filtered down to logistics. More frequent recoveries reduced the need to keep aircraft aloft as long, saving fuel and lowering airborne fatigue. In short, the angled deck converted a single-deck geometry change into an operational multiplier, affecting tactics, logistics, and the tempo at which carrier aviation projected power. As carriers adopted the angled deck, aircraft and deck systems evolved in parallel. Manufacturers increased hook travel and reinforced landing gear to cope with faster approach speeds and harder deck impacts. Arresting cables and purchase systems were re-engineered to handle repeated high-energy recoveries. Deck handling tractors and catapult routines were adjusted to the revised traffic flows. The angled deck also influenced elevator placement and aircraft stowage patterns. Designers sought to ensure wing-fold geometry and elevator clearances would not intrude into the skewed landing lane. These equipment and airframe changes were not dramatic one-offs, but incremental engineering responses, a series of small adaptations across multiple programs that together enabled jets to operate routinely from carriers without repeating the high loss rates of the early jet era. When the angled deck entered service, public headlines were rarely breathless. The change was technical, quiet, and operational, the sort of innovation that reduces accidents more than it produces spectacle. Naval periodicals covered trials, professional journals printed technical diagrams, and service obituaries later credited Captain Dennis Cambell with initiating the idea. Institutional histories differ in emphasis. Some highlight the Royal Navy's early trials. Others point to shipyard ingenuity or cross-national uptake. But the narrative is consistent, a low-cost, high-effect fix born of operational necessity. For sailors and pilots, the angle mattered in the simplest terms. Fewer nights praying that a bolter wouldn't become a disaster. For institutions, it was a lesson in listening to frontline officers and converting modest ideas into fleet-wide doctrine. The Korean War, 1950 to 1953, supplied a harsh laboratory for carrier innovation. Carriers on both sides of the Pacific were pressed into near-continuous flight cycles, close air support, interdiction, and cap patrols over an unforgiving theater. The angled deck's earliest operational value was not theoretical, but immediate. Carriers that could recover and launch with less deck downtime maintained higher sortie rates during intense strikes, and the safety margin for bolters reduced the operational cost of aggressive recovery cycles. Pilots returning from night interdiction runs or battered strike packages found the angled lane a pragmatic ally. A missed wire no longer meant a cascade of parked aircraft losses or a halted air group. In action reports and deck logs of the era, shipboard officers recorded fewer multi-aircraft deck catastrophes and steadier recovered sortie counts, evidence that a modest geometrical change could sustain combat tempo under pressure. Once the angled deck proved operationally useful, the institutional machinery took over. Training commands integrated new approach profiles into syllabi. Carrier landing practice areas ashore painted angled lines and erected simulated LSO's perches. Shore-based rigs and early motion trainers incorporated go-around drills at higher approach speeds and steeper glide slopes. Instructor cadres standardized bolter calls, radio procedures, and emergency disciplines so that a pilot's instinctive reaction matched deck geometry rather than a legacy straight deck reflex. The procedural codification mattered. Innovation failed if humans could not reliably execute it. By converting practice into regulated procedure, navies guaranteed that the angled deck's safety benefits were not left to ad hoc judgment, but became part of routine professional skill. A quiet cultural shift as important as the steel and rivets fitted at the yards. The angled deck became a defining visual and functional element of post-war carrier architecture. It reshaped elevator placement, island location, and air group stowage patterns. It also freed designers to accept faster, heavier aircraft because the recovery regime had a built-in safety outlet.
Over subsequent decades, the angled deck's geometry persisted through retrofits and new build designs, becoming a near universal standard across fixed-wing, conventional takeoff carriers. Its legacy is pragmatic rather than rhetorical. Fewer catastrophic deck pileups, more reliable night operations, and the practical ability to keep air power afloat in sustained operations. Where once straight decks constrained jet operations, the angled deck removed that constraint, a small geometric tilt with outsized consequences for naval aviation's post-war trajectory.
Adopting the angled deck required more than shipyard hours. It altered maintenance rhythms and spare part flows, reinforced deck structure, relocated elevators, and modified arrestor engines, increased certain depot-level workloads, yet the operational payoff changed the calculus. Fewer multi-aircraft deck incidents reduced long fleet-disrupting repair periods and the heavy logistic tail associated with major fires. Fewer replacement airframes lost on deck, fewer extended repairs to hangar and flight deck plating, and reduced need for emergency spares. Supply officers recorded a shift. Short-term retrofit costs were offset by lower catastrophic loss expenditures and tighter sortie sustainment. In effect, the angled deck replaced an unpredictable high-cost risk, deck conflagration and mass airframe loss, with predictable, manageable maintenance tasks, an economic as well as a safety improvement for carrier task groups.
The angled deck's impact radiated beyond the carrier's steel. Escort patterns, cap rotations, and even destroyer refueling schedules were adjusted to exploit increased sortie capacity. Carrier task group commanders could sustain higher air presence over littoral zones, permitting tighter fighter cover for convoys and more persistent interdiction patrols. Higher sortie rates required better coordination with radar picket ships and reconnaissance platforms to provide continuous targeting information. In combined operations, Allies synchronized recovery windows so multi-carrier groups could surge combat air patrols in rotation without mutual interference. Thus, a modest deck geometry change translated into doctrinal refinements across the task group, a tactical multiplier that altered how naval air power was apportioned and sustained in prolonged engagements. Numbers and doctrine tell one story. Sailors' recollections tell another. Fleet oral histories, pilot memoirs, and LSO recollections from the 1950s and 1960s consistently frame the angled deck as a practical lifesaver rather than a headline innovation. Pilots describe the moment they first practiced a deliberate bolter and returned to land safely. LSOs recall rewriting hand signals to match a skewed horizon. Deck crews remember fewer mass fire drills and more routine single aircraft recoveries. These personal testaments, measured, rarely boastful, anchor the technical record to lived consequence. Nights in the dark when a missed wire no longer meant a catastrophe, or weeks at sea when the air group could sustain operations without the paralyzing risk of a deck conflagration. In aggregate, those quiet voices explain why navies institutionalize the angled deck, not for accolades, but because it worked, consistently and simply.
Once the angled deck's utility was proven, navies faced scheduling choices. Which carriers to retrofit first and which to reserve for new build designs. Retrofit timetables reflected operational priority and industrial capacity. Older fleet carriers received painted trials and temporary sponsons to validate geometry quickly. High-value frontline units were prioritized for full structural alteration during scheduled overhauls. New carrier designs, meanwhile, incorporated the angled deck from the outset, obviating retrofit costs. The pattern created a phased fleet transition. Within a decade, many frontline carriers sported permanent angled decks, while second-line units retained straight decks until major refits. Shipyard records and refit logs show a pragmatic sequence: trial, temporary rig, retrofit, then incorporation in new construction, balancing wartime readiness with long-term fleet modernization. Naval leaders routinely weigh material costs against human life and mission effectiveness. The angled deck presented a clear calculus: modest steel, dock time, and engineering risk versus the repeated tragedy of deck pileups and pilot fatalities. Command-level memos from the era reflect this ethical trade-off. Arguments for retrofit emphasized mission continuity and the moral imperative to reduce avoidable loss of life among trained aviators. Budget officers tallied retrofit expenses and longer-term savings from fewer catastrophic repairs. Flag officers emphasized operational readiness. The decision to adopt the angled deck broadly speaks to a service culture that privileged sustainment of human capital alongside fleet capability, an institutional choice to invest in a preventive design rather than intermittently respond to recurring catastrophes. As Cold War alliances matured, interoperability became critical. NATO navies exchanged doctrine and technical standards so that coalition carriers could operate compatibly during combined operations. The angled deck's near-universal adoption simplified coalition logistics. Shared training syllabi, compatible arrestor and elevator clearances, and predictable recovery profiles reduced friction when carriers from different navies served together. Standardization bodies and bilateral exchanges codified recommended angles, safety margins, and LSO signals to ease cross-deck operations. In multinational task groups, the angled deck thus functioned not only as a safety device, but as a technical lingua franca, one geometric convention that made joint carrier aviation safer and more predictable across Allied fleets. The angled deck's adoption rippled into the defense industrial base. Arrestor gear manufacturers re-specified purchase lengths and energy absorbers to handle repeat high-energy recoveries. Catapult and deck handling firms revised tractor and elevator interfaces to align with skewed stowage patterns. Aircraft builders adjusted hook geometry and undercarriage tolerance tables to reduce post-landing maintenance. Shipyards and steel suppliers saw a predictable demand spike for deck plating and reinforcement sections during retrofit waves. Procurement offices managed phased contracts to avoid single-point bottlenecks, staggering deliveries, and prioritizing frontline carriers. The result was an industrial choreography: modest retooling and new part specs across multiple suppliers that collectively enabled fleets to scale the angled deck capability without large breaks in operational tempo. As carrier design evolved, faster hulls, larger air wings, and new launch and recovery systems, the angled deck remained a central datum.
Whether paired with steam catapults, hydraulic launches, or ski jump ramps, the principle stood. Provide a safe, non-fatal path for a missed arrestment and free the forward deck for parked aircraft. In STO bar and Cato bar variants, angled configuration influenced where islands were sited and how elevators were sequenced. Even as vertical short takeoff concepts and VSTOL aircraft emerged, the angled deck's geometry shaped how mixed air wings were stowed and cycled. In essence, the tilt became part of the language of carrier architecture, an enduring, flexible design choice that accommodated successive technological waves rather than being superseded by them.
Popular accounts often quantify the angled deck's benefit as an 80% drop in carrier crashes, a vivid figure that circulates in documentaries and retrospectives. Such round numbers function well in narrative shorthand, but risk compressing varied metrics into a single statistic. The historical record supports a clear, large reduction in multi-aircraft deck collisions, fewer conflagrations, and higher safe sortie throughput. However, different navies and researchers measured outcomes differently. Incidents of deck fires, pilot fatalities, class-wide loss rates, or sortie loss ratios. Consequently, the precise percentage depends on which baseline and time window are chosen. The responsible reading, the angled deck produced a substantial, demonstrable safety and operational improvement. Single-figure quantifications should be treated as summary indicators rather than immutable, universally applied facts.
By the time Cold War carrier fleets reached maturity, the angled deck had passed from experiment to expectation. Its legacy is not a single headline or a single medal. It is the steady recalibration of risk across millions of carrier deck recoveries. Fleet logs, pilot recollections, shipyard timetables, and training manuals collectively show a clear pattern. Fewer multi-aircraft deck conflagrations, more consistent night and high-tempo recoveries, and an operational architecture that permitted jets to operate from sea with survivable failure modes. The angled deck did not eliminate accidents. Aviation is inherently risky, but it converted many once catastrophic outcomes into recoverable events. That conversion reshaped carrier doctrine, industrial practice, and the lived reality of sailors and aviators. In technical terms, a simple geometric offset changed the error state of naval aviation from fatal cascade to manageable incident. And that engineering shift, quietly enacted in yards and briefing rooms, changed the shape of naval air power for generations. The historical record supports a decisive, demonstrable safety and operational improvement after the angled deck's adoption. Fewer cascading deck disasters, higher sortie throughput, and better night operations. The oft-repeated 80% reduction is best read as a strong, memorable summary of wide-ranging improvements observed in post-adoption fleets, not as a single universal statistic applicable to every carrier class, navy, or time window. Where precise metrics are needed, for scholarly work or a technical briefing, cite the specific incident categories, time frames, and fleet baselines being compared.
If you found this documentary useful, subscribe for more verified naval history. Like the video to support research-led documentaries, and share it with someone who loves military aviation.